So I didn't really have anything topical to hand out, and so I stole what my dad does with his 11-year-olds in church, and I brought candy.
Yeah.
So if you ask questions, give comments, you can have Snickers or Reese's. So. So I'm talking about genetic algorithms harnessing the power of Darwin, and unfortunately this one has a little bit of background, so it'll be a little bit of a PowerPoint presentation before we get to the fun examples.
Thank you.
So, and so Act 1, the objective function. So I guess I should give an overview, but so so this is part of defining the problem of genetic algorithms. What can you apply them to, right? And so at first we have an X, right? And this represents, so you need to come up with some, I'm talking very generic here, but I'll come to examples in just a second, okay? And so we have a problem that we need to solve. And then the X is a solution to that problem, right? And the solutions can be a wide range of different things. They can be continuous, discrete, unbounded, complicated data structures, vectors, but the solutions must be breedable and mutatable, and I'll explain that in a second. And then we need a function, f, that evaluates how good of a solution it is to the problem. And f needs to produce a number, which is how good it is. And if you can make your function evaluation efficient and automated, it'll be much, much better. Actually, most of the runtime in codes like this are going to be spent just evaluating how good a solution is, not even setting it up and doing all the genetic, all that stuff's computationally simple compared to is it good or not. And so examples. So, like for instance, one classic example, this is the traveling salesman problem. I said this is as a best delivery route. And so your X, this is a solution, is a order list of how I want to go through and visit all the cities I need to visit for my deliveries. And then your function, how good that solution is, could be, the number of miles driven or the number of time taken, all sorts of variables like that. And so for a given route, you know how good of a solution it is. Since we're dealing with Brewery Buddy, I also says, if you wanted to find out a brewery schedule, you could have X as a list of beers to be brewed in the order that they're in. And then f of x could be the utilization. And this could have all sorts of variables, like some of these beers can only be brewed in these hoppers and vice versa, and some of them have to go for longer or shorter. And so there can be all sorts of variables about how you define that. As long as you can calculate them for your objective function, that's fine, right? And so you might want to start a beer that takes 3 days on the weekend on Friday, because if nobody works during the weekend, if you take one that only takes a day, you're going to waste a lot of time. So another big example is neural networks. And I'm not going to go into neural networks, but in the basic, all these connections have a weight to them about how much the next layer trusts each node coming from the previous layer. And so this comes down to a huge number of weights, and when you train a neural network, you're just optimizing that. And so your X becomes a vector of node weights, and that could be thousands of node weights or even millions in some instances. So that's a giant vector. And then your function of how good is that is how well does the neural network, how many errors does the neural network have on a set that I know what the outputs should be, right? Questions? Okay. And so this is an example that Tarakesh gave me, which is using neural networks about how to learn to walk. And in this case, X would be how do you respond to the different inputs. And then f of x would be, let me turn the sound off here. And then f of x would be how far it goes before before falling over. And you can see in this case that it's getting better over time. That shows that your f of x is improving, right? Mm-hmm. And and so another example is, this is what I did at my previous job, is physics simulation modeling. And so you have X as a vector of experimental parameters, like you have an accelerator. Well, what's your beam energy? What's your beam energy distribution? What's your divergent? How is your have your detectors moved off their calibration point? And I put tides in there because I was amazed at some accelerator laboratories like Brookhaven, their detectors are so sensitive that the moon changing position changes the gravity just a little bit, and they can pick it up in their detectors. And so, what you do is you say, well, I think I know what the beam energy is, but I can't measure it very accurately in the middle of experiment. So I'm going to look at the experimental measurements I have, and then I'm going to work backwards and use genetic algorithms to try to figure out which experimental parameters give me those outputs. And then you can use genetic algorithms to mix your inputs together to minimize how much the error is, how closely it matches the model. And then in biology, X is the genetic code for the algorithm. That's going to be your DNA, and then f of X is how likely it is that you pass that on to progeny. So this is what Darwin kind of figured out. So we have the function the objective function that says how good is this, and then we have the sets. But the real power of the genetic algorithms come in how you take those sets and combine them to find new ones, right? This is the genetic modifications. And so the first one is mutation. And so this is randomly change X to create a new one. And this mimics how in biology you just get random mutations, a cosmic ray hits your DNA, and boom, suddenly it's different, right? And so this one can come up with new solutions instead of just mixing existing solutions. You could get hit by a cosmic ray and your DNA will suddenly have something that has never been seen before in the human race, and that might be better, and you might pass it on, and it might improve the population. And so this is an important thing for exploring new areas rather than just kind of remixing existing solutions. And so like in the delivery route, you could just randomly swap new cities or move a city to a new position. And that may have you driving from, your solution might have been to drive from, New York to let's say Baltimore, right? And you may swap this and suddenly you're driving from New York to Los Angeles and then to Baltimore. And that's obviously not a good solution, but at least you explored a new area. You might randomly swap two cities, same thing with the brewery schedule. You might just, say, hey, we're just going to try putting this one up here. And it's fine if they don't work. This happens all the time. But it's worth the cost to explore new areas sometimes by trying these. In the neural network, in the physics simulation, you can just randomly change one of those values. You can just look and say, hey, what if this weight was 200, or what if the beam energy was 20? And then look to see if that helps your model or hurts your model. In the Walking algorithm, you have basically a vector of inputs, and then what responses should have to those inputs, right? You could just randomly say, well, instead of moving the leg up when we do this, move the leg down, and we'll see if that makes it any better. So the other type is sexual reproduction. I was tempted to get a little sound sample, but it's not.
It's all in our head.
Yeah, that's what I do. And so this is where the real power comes from. Is the mutations will get you a certain amount of the way. You can make small modifications. You can kind of move around an area and see if that's the best. But to get big changes, this is one of the best ways to do it. And so basically, you take two states. I'm going to call them X and Y, and then you mix their genes together in a way that creates a new solution. And so in biology, this goes back to 10th grade biology or whatever. You have vectors of genes, X1 to Xn, and so you randomly cross parts. And so here you can see that, X keeps the X1 to X10, and suddenly it gets the stuff from Y. And then, another chunk it gets the stuff from X, and vice versa. So it just is randomly swapping the stuff back and forth. And if you have this type of thing, it's helpful if the order of the genes is somewhat related to what they affect, right? It's like if we were looking at the physics one, it'd be helpful if this was like beam energy and beam divergence, because they're more likely to get swapped together than not. But that that just helps a little bit. It's not completely necessary. And so like on the delivery route or the brewing schedule, here's an example where if you have X and you want to move Y into it, you can just take this chunk, insert it into a random part of X, but then you have the problem where you might be visiting New York twice, and so you can just eliminate the previous one to New York. And this is a pretty big change of the schedule, but the thing is at the point you're moving in, this is probably somewhat optimized. This could really increase how things, how it works. So this would work for the delivery route, for the brewing schedule. They're both kind of the same problem, and so this is how you would mix them for that. And then in the physics simulation, the neural network, it's pretty straightforward. Where each of these are just a long array of numbers. You can just swap the parts in the middle, keeping the position. And so then we come to, so we have the sets. We know how to tell how good they are. We know how to breed them together to come up with new ones. And so the question is, how does all this come together? And this is the evolution stage. And so, it's Darwin there. So we create a population of randomly generated individuals. This is our initial population. We test those individuals for fitness, and then we cull the poor performers, and then we take the ones that are good, and we do things to make the next generation. And I have code that I'll show you for the stuff I was doing, where we, you take the two good ones and you mutate them, move them to the new generation. You breed them with each other, put the offspring in the new generation, and then you go back to number 2 and you test the new generation to see how good it is. So,
nice go-to, by the way.
I was really tempted to, instead of numbering these like that, to put 10 like basic. Yeah, 10. So that's it for the PowerPoint. Now I want to show off some of the work. And
that's a boy.
That's actually a Z.
Oh, okay.
But we'll get to that in a second. So I haven't had a good chance to prepare this because literally as I was driving over, it was still running these simulations on my laptop. Man. It takes a couple hours to go through, and see again, the actual genetic code. I'll show the code in a minute. The actual genetic code isn't that bad, but the OCR takes a long time. So.
Which is your evaluation function? Is that right?
Okay, so yeah. So let me zoom in here. Actually,
did it come up with the alphabet?
So this is the final alphabet I came up with.
Oh, okay.
Oh, cool.
Yeah.
And I should be actually. This is a better one to show.
So the computer came up with that?
Yeah.
So what happens is, and you can see this on some of these. You can see like I started. These are a little bit out of order, but I started with pretty big. It randomly choose. So it goes through letter by letter, and it comes through and says things like, "I want to make a 6." Okay, and so it randomly chooses it seeds that initial population with like 12 different fonts of 6, and then it takes those and then runs them through the OCR program, and it gets a fitness out of the OCR program about how good it can recognize that 6. Mm-hmm. Okay, mm-hmm. And then the 6s that are good, it takes those and crossbreeds them and makes the next generation. And I specifically made it so that at the early part, it adds a lot of noise. It starts mixing in random new fonts and things like that. And so you can see as the generations go, this is the best one of each generation. It kind of gets kind of wacky, but it's also something that the OCR will recognize. And so I think this kind of gives it a nice effect because, you and I can still recognize it because the OCR can recognize it, but it looks very, very different from what you would think a font is. And if you look at these, you can start picking out some interesting things like, I should make this bigger so that the viewers at home can see. But like on the, if I was thinking about this in like the Qs, you can see that the Qs, the capital Qs keep a very definite tail as they're coming across, because that's the defining feature that if the OCR was marking these as O's, it would throw them out of the population. And then the last one that I think is really interesting is if you look at these Z's here.
Oh yeah, this last one was 2 slashes.
Yeah, because the OCR doesn't care about the top slash of the Z. The top slash doesn't tell it if it's a Z or if it's a 7. It's really interested in the bottom slash, and so it just kind of forgets about the top slash as it goes along.
So as we look at this, we're probably actually what we're measuring is how good the OCR is from our perspective, I guess.
Yeah, see, that's the thing is, I mean, I could make it where it takes two fonts, mixes them together, and you look at it and say, is this good or is this bad? But that'll take you hours to sort through saying, which ones do you like, which ones do you not like. And so I have to kind of fib and I have to substitute and have the OCR program do that for me.
That's neat.
And so if we look here, oh yeah, like if I, showing off the Z's, right here we can see the Z's as they progress through the generations. This is the first generation, so it's had a Z, and then it added a second Z down there, which gives it that weird second bar. But you can see over time it starts getting rid of the top bar, and the OCR still thinks, the OCR, well, it doesn't think this one's very good.
What are the scores next to it?
The scores are 0 for these ones actually.
Bad Z.
Yeah. The last number is the score, and sometimes it takes some tweaking, and I didn't have a lot of time to tweak. So,
What is the best score?
this best score. So the scores are this last little bit of the number. So the score of this one is 10, and that's out of 20 for this batch.
Bad A.
Yeah, and you can see that one. That one kind of went down.
It
to
looks
0
like a
again.
dinosaur at a desk.
Bad B. Oh, it could be.
Yeah.
Better B.
And see, like I said, this one, it likes this one a lot. It scored at 17 out of 20, and that's pretty mangled for a B.
Yeah.
But, I guess the OCR says, well, there's a circle and there's this is kind of reverse engineering the OCR. So the code, and this is kind of ugly Python code because it was highly experimental. I'll come down here, and it uses a lot of randomness. So right here, it goes through and it takes some random fonts and sample. It runs through every single letter. It grabs a random font and adds it to the samples, and then you can set. Like for the batch that I was showing you guys, I ran with 12 with a population of 12. And then I ran for 12 generations. And, honestly, I'd like to run a lot larger population. I'd like to run a larger generation, and I'd like to do a more detailed OCR. But this was already taking like 4 hours to run on my laptop. And, when I didn't finish the program until this morning, I didn't have a lot of time to... and so I come in, I randomly fill it, then I score it. I have a function there for that, and then I just keep on going through each generation, and I score it, and then I make a new generation, and do some printout stuff in the middle to save the files that we're looking at. So here's kind of the meat of it is the make new generation, and one of the parameters I added was this heap parameter, which is the percentage of the way done going from 0 to 1. And the idea is that when we have a new sample doing this wide open area, we want to be really, really aggressive with messing things up. And as we get closer to the end of it, we don't want to mess things up as much. We want to kind of settle around a solution. And so, if we're 70% of the way done, it just copies the good ones to the next one saying, well, hey, if we're this far and we're not getting any better, we'll just keep going with what we had before. And then it also just takes these, and this is a mutation where it just takes a piece of it and moves it a little bit inside of the image. And so again, this is what it's doing. What it's doing pretty high up there is just modifying these a little bit. Down here where we say if we're less than halfway through, it's right here. It takes a random font. It takes a random font, pulls that letter, and then crosses it in. And so when it crosses it, we have a 48 by 48 grid. It literally takes this one and this one. It chooses a square, plops it over here, and takes what was there and plops it over there. And you can see that on the Z where you had the double bar. That's because it took the double bar from a different one and plopped it there. Even though it made no sense, this is the kind of thing with genetic algorithms. So, so the operations I have here are to cross, to just take a square from one and paste it into another. That's a mutation operation, and then the fitness. So for the fitness, I wanted to not just evaluate the numbers themselves because that doesn't give you very much granularity. And so what I did is I pasted them into a long image like this, added a bunch of noise each time I pasted, and this shows how noise resistant they are. And so the OCR would actually see this string when it's evaluating how good the Z is, and there's noise added each time for it to try to kind of work around. And the first reason why I did this is the OCR program didn't want to evaluate a single character. It wanted a wide string of characters to evaluate. And then the second reason is if I put up 10 or 20 samples, it might only get 18 of them, and that's good because if I put up 20 of the same sample, it'll probably get all 20 or get none, and that doesn't give me a very good middle ground about which ones are best, better, worse, and worst. So, and then just let me show you the actual. So this is these two functions. This is the cross random square. It just finds a span in X, a span in Y, and then, copies the pixels out to a temporary one and, swaps them. And then this one just takes a random square. Again, it has the span. It just makes a square, pulls it from the source and pastes it into the destination, and it can move it around up to 4 pixels, just to kind of muck with things a little bit. So, and then there's another one here. Make random mark that will just take a random. I didn't use this one in the populations I created, but it will just choose a point and then put a
Random color.
like a 5x5 square and plonks it down in the middle just to mess with things. So, questions?
So is that random mark how you were generating the noise?
No, the noise is just my scoring function.
I assume that too.
Where did I put that? My scoring function here goes through and it let's see here. It takes the image you pass in, and then for the OCR repeat, this is just how wide it makes that OCR image. It copies it over. It throws some noise on it. The noise function is just 5% of the time change the pixel value to the opposite. So, but the thing is that the noise function only happens to what's passed to the OCR. It doesn't go into the genetic lineage. It's just a function of making the OCR a little bit, giving the OCR something more to chew on. So
The OCR, was that pulled off the shelf, or is that just an existing library or something?
yeah, I'm using PyOCR, which ties back to the Google TestDirect library. So, but I didn't want to write my own OCR, so.
Yeah.
That's not.
But it's interesting if we look at the
Critical.
yeah, that's just my image viewing program complaining. It's kind of crazy here. So this is the log of the program as it runs, and it actually shows you what the OCR thinks. And you guys are cut off just a little bit there. And so, like right here, say it's running generation 10 of the small g letter, and these are all the members of the population, and this is what the OCR thinks they are. And so, let me see if I can make this video. So it comes out with all sorts of crazy stuff. Yeah. Like right here it says, well, this one is supposed to be a small g and it's returning this string, as that's a score of -19. But this one, and I didn't save all these intermediate images, but this one is a score of 16. And it, one of the G's I thought was a 3, but the rest of them were pretty good. So
So what it's printing right there is what it thought it was?
yeah, that's what the OCR returned.
Okay, and you pass like a long string of them each time?
Yeah, you remember that
Yeah.
long image? I passed that into the OCR, and so the
Okay.
OCR sees a image that's composite of
Mhm.
20 of the letter.
And it tries to recognize each one?
Yeah,
Cool.
it tries to recognize it as a long word, and to varying degrees of success.
Yeah, I wonder what the 3 one looked like.
Well, see, that one was G generation 11 with a score of 16.
Here we go. Cool.
So I
We can
think
see what the computer thinks.
that's right. G. So that was G. What generation was it?
I think you said 11?
11 with a
And
score of.
16.
So this is the letter I was evaluating.
Yeah, I mean, that's a yes, you know.
But still,
I kind of get a G out of it.
Yeah, I see a 3 too.
Yeah.
yeah, and we
The
look at this.
computer
Like,
doesn't know.
I see a ninja.
but see, this score.
He's a Rorschach test.
Yeah, exactly.
See,
See my mom.
See, well, how about you ask the question? You want a Reese's or a Snickers?
Snickers.
I
is
see a
good.
lizard jumping off of
Sorry.
off of like a cliff.
Yeah.
Trees over the line.
Give me that second.
Yeah, but I mean,
Chopped liver over here, Brian? That's too quick.
oh, you didn't remember? You want a Snickers or
Throw candy at
Reese's?
him.
Throw me some candy.
He's hungry.
Snickers,
He's a
yeah.
little hangry over there. Get them Snickers.
All right, I have a question too.
Okay. You want
So,
You wanted it.
so,
See through it.
so, and this is not related to, finding fonts and everything, but, so whenever, like the sports books, and they say, oh, we ran the simulation 70,000 times. Is this kind of what the 70,000 times of that simulation, they're evaluate, I don't know, it's almost different the way they evaluate it. I
So,
would
so,
guess.
so the sports books, they're not necessarily looking for the solution. They're trying to do a prediction, and so it's actually highly related because that's something called a Monte Carlo simulation. At the basis of a Monte, you can't really model something. You just, if you can't model something fully, you just randomly, 10 million times and times. And the average of those 20 times, if I had processing power, and I'll probably do this over the break, I would take the G and I'd run it 200 times to the OCR.
I was like, can we get the man some compute power?
I want you to carve the resulting, final last generation into stone, and then
This is a G.
500 years from now, Futurama's being filmed, and they find that, and they're like, look, it's the freaking alphabet, man.
This is the G. This is
Yeah.
the computer's G.
Well,
So the program generated all these files?
yeah, the program generates files as it goes along. This is the final alphabet I ended up with.
Oh, nice.
So this is the best example on the last generation for each of the letters.
Look at that G.
Yeah.
It's there.
I like it. I wonder if we could, the high five people could use it for their prisoner breakout. It's kind of edgy,
Well,
Which letter turned out the best?
Hey, nice.
I think the Y down there looks really good. The lowercase one.
Yeah, that was really
well, if you want creepy, I think the small M's pretty good. That kind of looks like it's dying as it goes along.
It's
I mean,
malformed.
you can see it's probably a font with a nice big M over here, and then it got swapped in with
Yeah.
one that has small M.
Oh, yeah.
So,
Oh, the J is not bad either. It's got a good stick.
well,
That big O.
But it's
Like
got
a
that
G.
extra.
yeah. See,
Yeah.
see, some of these are just kind of hopeless. Well, I mean, like
They
for
did their best.
well, for some reason, as even on the brand new small C's, I had a hard time recognizing them.
The C and the O.
Oh, is that why you and Holland were talking about OCR fonts? It was just having trouble from the get-go, just picking out some of the fonts.
Yeah.
That's a
So,
that's a bad O. Oh, that's the final O.
I'm not sure.
It looks better zoomed out.
Well, it kind of freaked out on me. So these are the letters I started with. And what's kind of interesting is there's some research in the late 70s, 80s, where they came up with OCR-friendly fonts.
Oh, that's the first O?
In the 70s?
I think it was like late 70s.
Really?
Wow.
And so this is what they consider an OCR-friendly font.
That was pretty friendly.
Yeah.
But the OCR had really big problems with some of the letters in here.
Really?
What was the issue?
Let me see if I can.
Some of them serifs and stuff.
I don't see a lot of serifs.
Yeah, it wasn't the serifs. I think the serifs are pretty easily removed by kind of defuzzing it. But like the Q.
Oh, that's why.
Oh.
And it could be because the OCR people says we want to make a O look different from a 0, and so it does things like this.
The computers were different then.
And the OCR programs now just kind of freak out about it. Like the G, it had a hard time with this G because it's looking for this and it's confused by the straightness.
Oh.
It definitely
So.
is.
Yeah.
So the future work that I didn't get to for this talk is I want to use these genetic algorithms to generate truss bridges. And so in that case, your X would be the structure of a bridge, and then your objective, so you create a structure of a bridge, you do a simulation to figure out how strong each of the members would have to be on that truss bridge, and then your objective function would be how expensive would this bridge be to make. And then your mutations could be adding links, deleting links, moving places where the links intersect. And the hard part is figuring out bridge sex, about how two of them exchange information and still create something that's somewhat viable.
For a second there, I was like, did he just say bridge sex?
That's how they make new bridges.
That's right.
So,
Could this be applied to some other use cases like, right now you're doing OCR, but say like there's audio or other types of analysis where it's kind of like fuzzy problems and it seems like the algorithms are really still struggling.
well, so there's a lot of work on like having computers generate music and things like that. The hard part is your objective function. This is the hard part of any computational creativity. Like, you can have a computer make a picture or try to make a painting or whatever, right? How do you tell if it's any good? And unless you can have an automated objective function to evaluate that for you, like you think about, I had, even on a single letter, I had a population size of 12, and then I had 12 generations. That's 144 evaluations just to generate the one letter, and this is really kind of wussy compared to what I should be doing for a genetic algorithm. You can have computer, you can have a computer, across Mozart and Chopin, but how do you tell it's
You need
good?
a human ear to
Yeah, and
That's just like one of those cases where it's like subjective, like whether or not that it's good. Like,
well, but see, that's the thing is even if it's subjective, you still have to throw out some of the population and know which ones you should carry forward. And a lot of them. I mean, if we go to the raw data here,
The human algorithm.
a lot of these, if we just choose random ones, a lot of these are just crap. This one scored a negative 24.
Is that a 6?
But I mean, under your example of crossing like Mozart and Chopin, it could mean like harmonics or like keys or other things like that that don't clash. Like, could you set some sort of rule structure that would kind of help
Beats
it?
per minute.
Beats per minute.
Yeah, I mean, you could cross them and then, look, do they follow a chord progression or
Yeah,
things
exactly.
like that. But then you're kind of doing what I'm doing here, to where you're reverse engineering your evaluation criteria. And see, part of the problem is I came to the realization this is kind of a bad example because I start from really good data. The fonts I start from are really good fonts. The OCR is really good at recognizing them, and so I'm kind of mucking it up. I should have started from just straight lines
I'm
and
gonna
then
say-
try to evolve into a font. But again, that would have taken
Long time.
months to calculate on my laptop.
I'm gonna say you could take your newly generated font set and use that to see if
That's
you
right.
can
There you
get
go.
a really good one.
A copy of a copy of a copy.
Well, what I need to do is see if I can get the TextDirect library running on a GPU, and if I did that, this would go significantly faster for doing these evaluations, and I can play around with them a lot more.
Bitcoin miners, I got some GPUs.
Some GPUs.
That one got a negative 25 right there, right under it. What does that one look like? bad.
Yeah.
Bad little.
Well, and little o I think is a really bad letter for trying to do
Seems
the
like it'd be
calculations.
easy, but you know.
Or that's a 0 actually.
Oh.
Well, but see, that's the problem is your little. How do you tell a little o from a 0 from a C?
That's a good question.
You
Stuff
know,
like that.
I'll bet that when it's outputting those ones, it's outputting a lot of those other letters.
There was one that had a negative 33.
Yeah.
So is there a maximum for the negative?
Yeah, what's that?
So if we look back at what it thinks here, is it adds one for every time you get a correct one, and then it subtracts one for every time you get a bad one.
Oh, okay.
And so, some of these end up being like this one right here, that's scored a negative 25 because it's supposed to be an H, and yes, there's H's in it, but I think it thought the H's split apart and we had L's and I's together.
Oh.
So it thinks your H is actually an I and an L.
What can you do?
That's really going to tank the score. And I wasn't too worried about the negative scores. Once
Get rid of them.
yeah, there's some get rid of it. It doesn't really matter if they're negative 50 or negative 20. They're going to get trashed for the next generation.
Yeah.
So
You get to choose who reproduces and who doesn't.
And the positive go up to 20.
yeah, and
Like
well,
in the case
There's a
of G,
terrible joke.
it recognized all of it as G, but it still was at 18 something.
the NG, it was still at 18 because it still misrecognized 2 of those, even though that was the best one it came up with. There was actually some of them that got above 20 for score because it recognized the letter twice instead of once.
Oh,
But I didn't want to go through all the trouble of trying to sort that stuff
YouTube
out. So.
comment.
But those are pretty rare that it successfully recognizes what I want the letter to be is 2 of the letter I want it to be. So
Yeah.
Hey, put those goggles on, like the 3D glasses, where you see.
I guess maybe if I crossed an L with an L, there might be 2 L's in there or something.
Mm-hmm.
So
The screen is a little fuzzy because the system wouldn't run on Linux. So if you have any these resources that you want to share for our at-home audience,
yeah, I'm going to put the code up on GitHub. I'm going to put font examples up there too.
Cool.
So
so we can link that after the fact and
Yeah.
and the events link for anybody that wants to kind of dig into this a little more.
yeah, we should add it to the YouTube page and all that. And I do want to try to take that font one and actually make a system font out of it for the fun of it. So
Yeah.
We got a game studio that might appreciate it.
Yeah.
Just a very scary font.
I know what my new text editor font is.
A scary font.
And we're doing like demos and stuff, and they're like, "What are you writing?" And I can't.
Serial killer font.
We can type, get you some money, put like a $200 price tag on it.
well, no, but you're not thinking. You don't give a $200 price to sell this font. You give a $200 price tag, and I'll create you your own font.
Oh.
So
There you go. Business.
So.
Still an entrepreneur.
Mm-hmm.
All right. So any other questions or?
This is cool.
Yeah, it's awesome.
Yeah. It was a lot of fun to work on, but yeah, I wish it would have worked out a little bit better.
You didn't. I was,
Computers, man.
Well, it's kind of better if you don't know what's going to happen because it's more exciting when you're doing it. So.
If you do it again, yeah, I would just start with like the lines or whatever, just like really bad font, Or yeah, you could take like the font that it came up with and then run it through it again and see what it does.
Well, I thought about like taking a capital A and then trying to train it to mutate that capital A into being a small lowercase m.
That would be really cool.
And then so just use the wrong letters as an input source to try to find the pieces to make a font. But you would need
A lot of time.
you need a you need a population size of like thousands in order to pick out a couple that might be somewhat good in order to get away with that. So.
this sounds like something that some of us would do. We would just put Dylan's face as the start of all of that. Just evolve that into like the
See,
different
it turns
things.
into an A.
All right. Well, on that note, let's thank our speaker.